Hello, I am Makarand, and my PhD thesis is on comprehensive investigations into electrical characterization, converter topologies, and electromagnetic forces in wire EDM for semiconductors. Wire EDM stands for wire electric discharge machining, and I have worked to extend its application beyond metals for slicing semiconductor ingots. I have worked with Professor S.V. Kulkarni and Professor H.J. Bahirat at the Department of Electrical Engineering, Indian Institute of Technology, Bombay, Mumbai in India. This presentation will cover significant contributions of my PhD work. Let us compare the conventional technique, which is wire saw, with wire EDM. Wire saw is an abrasive process where the wires actually touch the workpiece to cut it, whereas wire EDM is a non-contact process where there is a spark between a metallic wire and a semiconductor workpiece, and heat is generated due to the spark, which cuts the workpiece. The minimum wafer thickness achievable with wire saw is limited to 180 microns, whereas that with WDM we can cut wafers as thin as 120 microns. These wafers are more efficient. Kerf losses are more in wire saw, and they can be reduced to 15 to 20% in wire EDM. Also, the surface roughness is more in wire saw, and it can be reduced in wire EDM. The machinability of a material depends on the hardness of the material, and harder the material, more difficult it is to cut with wire saw. Whereas here in wire EDM, the cutting is happening due to the spark, and hence its machinability is not dependent on the hardness. This is particularly useful for semiconductors like silicon carbide. Although wire EDM has all these advantages, there are certain challenges, like physics of the process is unknown because there is a metal to semiconductor spark, whereas wire saw is an established process and there are several models available. Also, the optimum process parameters are already available for wire saw. It is widely used in the industry, whereas the wire EDM machines commercially available are designed for cutting metals, and hence there are limits to obtain the optimum set of process parameters for cutting semiconductors. There is an issue of efficiency computation in the case of EDM pulse generators, which are used in the wire EDM. The efficiency computation is not addressed in detail until this point because the efficiency may not be that important. However, when it is used for semiconductor cutting, the wafers will go to solar and microelectronics industry. The cost and energy involved in the cutting might be reduced if we improve the efficiency. The throughput in case of multi-wire saw is huge, like thousands of wafers per day, whereas commercially there are only single wire EDMs available and no multi-wire EDM is commercially available. So there are certain engineering challenges which need to be addressed if we want to realize multi-wire EDM. The first challenge is to explore the physics of the process. It is done by considering the spark current voltage or IV characteristics of silicon and comparing them with the steel. Systematic experimentation with the help of Taguchi methods is used, and experiments are designed considering five factors, and the recorded voltage and current pulse trains are observed. So the important observations are the voltage in case of silicon is more than that for the steel. Then the current for the silicon is lesser than that for the steel, and energy consumed by silicon is more than that for the steel. Another important observation is the ratio of currents is 1.5, whereas the ratio of the conductivity is measured by the four probe tests, particularly the electrical conductivities, is of the order of 10 raised to 5. So it is clear that it is not the bulk electrical conductivity which is responsible for the spark current observed. So there must be some non-linear element, and the representative circuit is not linear. Also, it is shown by a statistical analysis that this voltage difference observed is not due to that electrical conductivity, but it is due to the junction between the plasma and the semiconductor. Let us see what is that junction. When we have wire EDM of semiconductor like silicon, so the silicon is placed on a metallic workbench, and then pulse generator Vs supplies the pulsed voltage to the wire and the workpiece, and then a plasma is formed as shown by this yellow uh, part here. So this plasma and silicon forms a metal to semiconductor junction because plasma has so many charge carriers, so it is considered to be metal like. So there is a metal to semiconductor junction, and here there is actual metal to semiconductor junction between the workpiece and the workbench. So these are two diodes D1 and D2 in the equivalent circuit which is shown here. As you can see, the circuit in case of silicon cutting is having two diodes in addition to the circuit in the case of metal cutting. So this difference in the circuit is used to explain the difference in the voltage, and it is shown that it is not the diode D1, rather the diode D2, or the metal to semiconductor junction between plasma and silicon, which is responsible for the observed voltage difference. The next issue addressed is that of EDM pulse generators, namely EPGs, and the two problems addressed are modeling and efficiency improvement. So this is the circuit topology which is chosen, and its modeling is done considering three stages of operation, that is the pre-breakdown, sparking, and pause stage. So there are three different circuits and three different transfer functions which are shown to exist. Then efficiency computation is done in detail considering three stages of operation and equivalent duty ratio calculation, because there are two frequencies. One is the pulse repetition frequency and the other is the switching frequency. It is found that the efficiency is very less. So we have proposed a new pulsed current reference scheme as against the constant current reference scheme where the current is kept constant. So here we reduce the current reference when there is no sparking or cutting taking place. So that results in an improvement in efficiency of the order of 30 to 40%. The pulse generator is also implemented in hardware, which is shown here, and the hardware results also show that there is a significant improvement up to 30% in the efficiency of the pulse generator. Another important contribution of my work is making this customizable miniature wire EDM or mini WDM. This is a complex electromechanical system which was completely designed, developed and fabricated in-house. It consists of 5 subsystems: CNC, tank plus workbench, wire feed subsystem, pulse generator and dielectric circulation system. All these systems were designed and fabricated in-house. You can see the cuts obtained in the silicon workpiece observed through rapid eye microscope here, and the kerf losses are compared in this table. You can see that the commercial WDM and mini WDM, the kerf losses obtained with these two machines are comparable. Also, the important points about this mini WDM is that it is low cost and miniaturized. So it is useful for engineering institutes, research institutes and small scale industries and other industries which cannot afford the large space and cost involved in the commercial available machines. Another important issue is that there is no multi-wire EDM available. What is multi-wire EDM? There are several wires like W1, W2, W3 up to WN as shown here, and it is shown for the first time that there exist wire-to-wire forces so that the wires will bend like this, shown for the 5-wire EDM as a test case. An analytical expression for the force is derived, and how these forces will affect, we can have a wafer surface which is not plane, it is uneven or it is not perfectly flat. Also, this can increase the effective kerf losses. In order to tackle this, we have to exert tension of the order of 85 to 90% of the failure strength as reported by the previous researchers. So, we have proposed novel schemes which can reduce the tension to 20 to 40% of that required in the present schemes. So, how will this help? This will reduce the wire breakage and it will reduce the kerf losses. Also, the pulse generators circuit topologies which are required for these schemes are also proposed in this work. So in summary, I have worked in the experimental work in manufacture engineering, which consists of characterizing WDM sparks for silicon and comparing them with the steel. Taguchi design of experiments was used and nonlinear nature was investigated. Then in power electronics, I have modeled and proposed a new efficiency improvement scheme for EDM pulse generator. In the case of electromechanical systems, I have designed and fabricated customizable miniature wire EDM machine. I have also worked in electromagnetic analysis where I computed the forces in case of multi-wire EDM and proposed new schemes such that the machine becomes more robust. Thank you.